So, hi everyone. My name is Liat Shenhav. Can you hear me well? Good. I'm a new PhD student in Ran Halperin's lab. Therefore, I'm going to present my previous work, which is a joint work with Professor Ruth Heller and Professor Yoav Binyamini from Tel Aviv University. And I'm going to talk briefly about my current research interest, mostly, in the last two slides. Right now, it's a little bit different from what you've heard until now. Hopefully, it'll be interesting. So I'm going to talk about replicability, actually, and specifically in systematic reviews. Systematic reviews are, in fact, just an aggregation of a lot of meta-analysis. So if you're not familiar with this term, meta-analysis you probably know. And I'm going to introduce a way to quantify replicability by using a term we call the R-value. So when multiple studies that examine the same problem are available, they're often combined in order to, A, increase statistical power, and in order to get a better estimation of the parameter of interest. And this is actually the graphical representation of a meta-analysis. It's called a forest plot. And this is meta-analysis, whether it's a fixed effect model or random effect model, it's usually the most common way of combining similar studies that examine the same outcome. They have the same test statistic. So here, every row corresponds with an independent study. We can see the cohort size. We can see the hazard ratio, the standard error. We can see the statistic. We can see a summary statistic for each study. And the important thing is the combination, the summary effect, which is actually an estimation and a confidence interval. So here we see this is a combination. This is actually was taken from Cochrane collaboration. I will elaborate on that in a minute. What exactly are the systematic reviews that we've looked at? But this examines, for instance, a way of giving chemotherapy, whether it's sequential or in a combination, and we see that it favors one side. It favors the sequential side. So what's the problem? It sounds really good, right? Gaining statistical power, more accuracy in our parameters estimation. So the problem is that the significant finding in a meta-analysis is often interpreted, and again, where we're focused on medical research, it's often interpreted to mean that the result is consistent across studies. Otherwise, we wouldn't have done that. We would have combined these studies. But in fact, we will see the reason to that in a few minutes, the significance may be driven by only one study. And in the example that I've just shown you, if we're dropping out the 7th study, what we're actually getting is a non-significant result, meaning there are 7 studies that indicate that there's no effect, actually, or not a significant effect, and only one study that drives the entire conclusion, which is worrisome, because there's no way that an investigator or a doctor or even a statistician would have known how to interpret the results other than the fact that they're significant. So what do we suggest? I don't think that we should stop using meta-analysis, but I think we should we should look at another perspective of that. We should add the extent of replicability across studies, because this is an information that is missing at the moment. And it's not a vague concept, looking at replicability. It's actually something that we can quantify. We suggest quantifying it by using the term we call R-value and a sensitivity interval, which is, it will be a replicability value, which is similar to a p-value. And I think it'll give significantly more information in regards to what we're looking at. Let's talk a little bit about the framework of the meta-analysis briefly and why it actually happens. So under the fixed effect model, what we actually have, we assume that there's one true unknown effect, which is theta, and the observed effect in every study. We have n studies, so I is the denote for the studies, and there's just one common effect and some sampling noise which is specific to each study. And the summary effect is our estimate of this effect, this theta hat. The way we do that in the fixed effect model, the summary effect is estimated by a weighted mean, where the weights are the inverse variance. And the variance is specific to each study, and the variance of the summary effect is just the reciprocal of the sum of weights. And the most important thing here, which is not written, is that the null hypothesis is that there's no effect in any of the studies. So I'm giving you a hint to why there's a problem here. In the random effect, it's a very similar setting, but now we don't expect one effect, one true effect. We assume that under the random effects model, the true effect was sampled from a distribution of effects. So we have the effect mean, or the distribution mean, which is mu, and we have psi, is it psi? Psi I, theta, whatever, this is actually the deviation between the true effect in study I to the distribution mean. Meaning if we're looking at it in the same way, mu plus zeta, mu plus zeta I is actually theta I, which is the true effect for every study. And we have some sampling noise. So we have another component of the variance. We have another noise, so if we're looking at the framework, what we want to estimate in this point is not a true effect, but we want to estimate mu, which is the distribution mean. We're doing it in the same way, weighted average, where the weights are the inverse variance, but now we have another component. We have the within study variance, and we have the between study variance, which is also a problematic issue, but I'm not going to talk about it now, which is estimated in the data. And again here, the null hypothesis is there's no effect. What is the replicability claim in this framework of meta-analysis? The replicability claim is actually that the conclusion remains significant, meaning we're still rejecting the null hypothesis of no treatment effect, but now we're not using meta-analysis, we're not using all n studies, we're using the n subsets of n minus 1 studies. And how this claim can be asserted if the meta-analysis of each of these n minus 1 studies will be significant. What I actually want to say, if we drop out every single study and the n minus 1 meta-analysis is still significant, it means that we have effect in at least 2 of the studies. So how do we, what's the key difference? The key difference is in the null hypothesis. The meta-analysis p-value tests the intersection null hypothesis of no effect at all in any of the studies. Sorry. And therefore, as I said, the meta-analysis can be significant, but only because of one study. And in this case, the meta-analysis claim can be true, and the replicability claim can be false. So what do? We offer this quantity that quantifies the evidence towards replicability. The R value is the maximum over n p-values, where p minus I is the p-value of the meta-analysis just without study I. And this actually, if we're claiming replicability whenever the R value is smaller than some significance level, let's say alpha is 0.05, it guarantees control over the false replicability claim, which the meta-analysis alone does not do. So very simply, let's look at an example. If we have 5 observed effects in 5 studies, so how do we do that? We calculate the p-value for every one of these 4 subsets, so without the first study, without the second, third, fourth, fifth, and so on, till we can actually calculate the maximum over all these p-values, and this is the R value. So if the R value is in fact significant, what the p-value means, it tests the null hypothesis that there's no significant effect except possibly in 1, meaning we have in at least 2. If the R value is smaller than 0.05, it means that we have effect in at least 2 studies. And this is the smallest significant level in which we claim replicability. So what is the application? We actually got to this, to looking at it by looking at the application first. So are you familiar with Cochrane reviews, Cochrane collaboration? It's an admirable organization that aims to make medicine better. It's a nonprofit organization. I think 130 countries are involved in. And they publish systematic reviews, which is a synthesis of a lot of studies. The systematic reviews are composed of, from a lot of meta-analysis, and they aim to make medicine less biased and less conflict of interest and more evidence-based and more evidence-driven. So therefore, the findings are a bit troubling, and I'll show you in a minute, because they aim, their goal is very important. And what their audience is actually patients, doctors, and policymakers, and they have a lot of impact and influence. So I'll show you two examples. This is a good example of a meta-analysis. This specific review, we focused on breast cancer. This specific review's objective was to assess the efficacy of a therapy with women that has some HER2 positive metastatic breast cancer. And here we see that they're combining 5 studies, and only one of them is barely significant. And if we're doing the sensitivity analysis I just told you about, and removing the most significant study, we're still getting actually the analysis, the meta-analysis is significant, meaning there is an effect in at least 2 of the studies, even though none of them now is significant. So we're gaining power, and this is good, and the R value indicates that. The R value is smaller than our significance level. On the other hand, when we're looking at another meta-analysis, that also from the breast cancer domain, we see here that different studies seem to have different effects. We have 8 studies here, which is not a small amount of studies. And if we remove study number 7, now the result is not significant. So I would want the doctor or the patient would look at study number 7 and not look at the entire result and see, oh, okay, so we should favor sequential chemotherapy and not combination chemotherapy, because maybe it's only relevant to Japanese, and maybe there's bias in this specific study. And it's definitely not across studies. So how prevalent it is? Unfortunately, vary. We've looked at the breast cancer domain. We've analyzed, according to some eligibility criteria, 21 out of their 48 updated reviews. And we found more than 60% of reviews that were sensitive to leaving one study out in one of their primary outcomes, meaning the R value was larger than the significant level. And 8 out of these 13s, all of their primary outcomes were sensitive to leaving one out, meaning that this is something that anyone who looks at a meta-analysis should be aware of. What kind of information they're actually what kind of information this is. And even though we account for another source of variability in the random effect model, it was prevalent similarly between the random effect and the fixed effect. So immediate and important extensions, because the single endpoint design, which I've just described, is rather rare. So accounting for multiplicity, since the R value are essentially p-values, we can apply family-wise error or FDR controlling procedures on the individual R values in order to account for multiplicity. So we can actually use that in bigger studies that have M outcomes and not only 1. And of course, we're not limited to looking at U equals 2. Maybe we want to be more conservative and look at replicability in U studies, which use when U is larger than 2, just as the procedure is a little bit, it's similar but a little bit different. Now we want to make sure that all subsets of U-1 studies actually have, the result is actually replicated in. So I hope I convinced you in the usefulness of the R value, not only in the Cochrane reviews. I think meta-analysis is a common method also in genomic data, and it is important. There's more work that relates to primary and a follow-up study with the R value from Professor Ruth Heller and Yoav Binyamini, that the application is specifically to genomics. So if you're interested, I'll be more than happy to talk about it. And what we are actually saying is the meta-analysis is not an evidence towards replicability, and the R value is exactly answers this question, this gap. So yeah, this is my previous work, and I would like to say a few words about my current work, because none of you will come to talk to me about replicability, I guess. So my current work with Eran Halperin's lab with Eran is very different. Is the development of time series methods in order to handle metagenomic and epigenetic data. So the data that we have now is very, very interesting. We have 60 timestamp of about 50 cows. We have their 16S OTUs, I hope I'm saying it right. And from birth to 6 months or a year. And what we would like to achieve is to estimate further ahead the unobserved data points, to look at the trajectories and the growth of how the OTU develops. We would like to maybe get using the epigenetic data to improve if we have phenotype prediction, which is based on one timestamp, to examine whether we can improve it with more than one timestamp, and possibly improve clustering. That's it.